Here's another example of writing Lewis structures for a compound. So this time it's H2CO. And some of these compounds that we're doing Lewis structures for are not compounds that we taught you how to name. So if you don't know how to name it, don't stress out. I wouldn't expect you to know. So the first thing we have to do is we have to make a skeletal structure for this, right? This one's a little more complicated. There's actually 4 different atoms, and so we have to decide what goes in the middle and what goes on the ends. Hydrogen has to be on the ends, it can't be in the middle. So we could start by perhaps putting carbon and oxygen in here together. And then let's try putting the hydrogens over here on the carbon. Oh yes, periodic table. Essential. Yeah. So there's our skeletal structure. We need to know how many valence electrons we're working with here. So we have 2 hydrogens, and they each have 1 valence electron. We have 1 carbon with 4 and 1 oxygen with 6. So that gets us 12 valence electrons to mess around with. The first thing we have to do is put a pair of electrons between the atoms to hold them together. So we need 2 electrons there, and 2 here, and 2 here. That used up 6. That means we have 6 left to give everybody octets or duets for hydrogen. So if we give carbon an octet like that, now we've got 8, 10, 12. We've run out of electrons, and we don't have an octet for oxygen. What do we need to do then? We need to share more. We need to make a double bond. So I'm going to put a double bond in here. That's the only place we could have a double bond. Hydrogen can't make double bonds. Hydrogen can only make 1 single bond. 2, 4, 6, 8, 10, 12. There's 12 electrons total. Oxygen has, well, let's circle it. Oxygen has 8 electrons, and carbon has 8 electrons, and each hydrogen has 2 electrons. Looks a little bit like a Venn diagram, doesn't it? So that's one way to show the Lewis structure. Another way is to use lines for those bonds. Now I put my lone pairs of electrons in different places, but that's okay. Any questions?
So the best way is to add it all up first?
Yeah, find out how many dots you have, how many valence electrons you have to work with, and then don't go over. You can't put in more than that. And if you run out, then you know you need to have multiple bonds. There was another question? No? Okay.
What decided that it was carbon in the center instead of oxygen?
That's a good question. And as I was doing that, I'm like, this is one of those things where they didn't really tell you enough. Because why not put oxygen in the middle? I mean, could we draw a diagram for that? Let's try it. Put oxygen in the middle and carbon over here and hydrogen and hydrogen. So just from the bonds now, I've got 2, 4, 6 electrons. 8, 10, 12. Again, that's not going to work. So we need a double bond in here. So could we do that? We could, but that's not correct. How would you know that? Well, you wouldn't.
So you won't have a test question.
I won't trick you with something like that on a test question, no. Okay. The, yeah, we haven't talked a lot about electronegativity yet, so I can't talk to you about that. One thing I can tell you is if we look at the Lewis structures for these individual atoms, so carbon has 4 valence electrons. How many unpaired electrons does it have in its structure? They're all unpaired, right? 4. It has 4 unpaired electrons, and it tends to form 4 bonds. If we look at oxygen, oxygen has 6 valence electrons. It's going to have 2 unpaired electrons. Do you see that? This one and this one aren't paired. These guys are paired, and these guys are paired. This is going to tend to form 2 bonds, and I can't see where I'm pointing. And the carbon with the 4 unpaired electrons is going to tend to form 4 bonds. And so that's probably the best thing I can tell you for you to have any clue why this one's correct and this one's not. In this one, oxygen has 4 bonds, and oxygen just doesn't do that. How could you know that? Well, what I just told you is really the only way. Here, carbon has 4 bonds. Let's look at this one, it's easier. Carbon has 4 bonds. 1 with this hydrogen, 1 with that hydrogen, and 2 with this oxygen. And the oxygen has 2 bonds. And that's what they tend to do. Carbon tends to have 4 bonds, and oxygen tends to make 2 bonds. But I won't try to trick you on that. Any other questions? Let's look at what to do with polyatomic ions. If you remember, a polyatomic ion has more than one atom in it. Those atoms are covalently bonded together, and then overall, the whole thing has a charge. So really the only difference between doing molecules and polyatomic ions is that we have to pay attention to the charge. If there's a negative charge, we have to add electrons. If there's a positive charge, we have to subtract. And then we put these within brackets and put the charge on the outside. So let's do cyanide ion. This is another diatomic. It's only got 2 atoms, and so then, then the structural formula, or the skeletal formula, is pretty easy. I mean, there's 2, carbon and nitrogen. They have to be connected to each other. How many valence electrons does carbon have? 4, and nitrogen has 5. And then what about that negative charge, -1 charge? Do we add an electron or subtract? We add 1. So we're going to add 1, and so we're going to get a total of 10 valence electrons that we can show in our Lewis structure. So there has to be at least 2 in there. So that's 2, 4, 6, 8, 10. That's not going to work, is it? Carbon's happy, nitrogen isn't happy. Everybody has to be happy. So that means we have to share. So let's take this pair and share them. We're getting closer. Carbon has 8 valence electrons in octet, but nitrogen has 6, which is better than it was. But this means we need to share 2 more. So now they're sharing a total of 6 electrons between them, and now they each have an octet. And then we would have to put brackets and the charge. The other way to represent this is with 3 lines. And then there's a lone pair on the carbon and a lone pair on the nitrogen. Brackets, charge on the outside. Yes, question?
Can they share 4 bonds? Or is it...
They don't. They don't. Yeah. It's a good question. If these particular two atoms shared 4 bonds, how many electrons would they each have? They'd each have 10, right? Because you count all the shared ones for each. So if we shared 4 bonds, well, one of them would have 8, the other would have 10. But it wouldn't be right. Any other questions? What's next here? Let's do ClO minus. What's the name of that? Chapter 5. Hypochlorite. It's hypochlorite ion. So Cl and O. Oops. So chlorine has how many valence electrons? 7. And oxygen has 6. And the negative sign means we add 1. Thank you. And so we've got a total of 14. So we have to put 2 here. 2, 4, 6, 8, 10, 12, 14. Helps to be able to count by 2s. Oh, look. We had enough. Isn't that nice? No multiple bond. And then we go like this, put brackets around it, and put a negative sign. The other way to do that is with a line and the dots. So like on the lab here where it says to draw Lewis dot structures, I will accept either style, but you need to be able to recognize both. Okay, any questions? Deathly silence. Okay, so the octet rule is lovely and all, but there's exceptions to it. There are some molecules that have an odd number of valence electrons. An odd number of electrons, period. And so it is absolutely impossible for them to have an octet. And so when we come across something like that, we just do the best we can. So nitrogen monoxide is an example of this. Carbon, there's no carbon in there, but nitrogen has 5 valence electrons, and oxygen has 6. 5 and 6 is 11. 11's an odd number. There's no charge on that, and so there's 11 electrons. So we could put them like this. So the nitrogen has 2, 4, 6, 7, and the oxygen has 8. Or we could write it like this. And that's really as close as you can get.
So would those molecules be really unstable?
They're going to be unstable, yeah. Yes?
Will the element that's closer out in full shot always be the one that gets the extra electron? Or could there be a case where nitrogen has a full shot, oxygen has...
We're going to talk about that in the last section that we'll get to on Thursday. That has to do with electronegativity. Some atoms are more attractive to the electrons than others. Oxygen is going to have more attraction for the electrons, and so it will get the extras, and nitrogen will be short. So that's one type of exception. Another one is compounds involving boron. Boron's a moron. It can't count to 8. Boron compounds tend to have only 6 electrons around the boron. Because boron's one of the little guys, right? He's not super little. He's like old enough that he should know better, and yet he doesn't. But anyway, he tends to have 6 electrons. I'm sorry, but that's what he does. So here are a couple examples. Boron trifluoride. The fluorines have octets, and the boron has 6. And he's okay with that, because he doesn't realize that he's only got 6. Here's boron trihydride. Again, it does the same thing. How many valence electrons does boron have? 3. It's in group 3A. He only has 3 valence electrons to share. If he shares 1 each with other atoms, then where would the extra 2 electrons come from? He'd have to find somebody who's willing to share 2 electrons with him, which does happen. It's called a coordinate covalent bond, but It doesn't happen with these guys. Hydrogen can't. So there are exceptions. Lewis model is not perfect, and yet it's still very helpful. Then there's another type of exception. Some atoms can have what are called expanded octets, so more than 8 electrons. So sulfur hexafluoride, here sulfur has 6 single bonds, giving it 12 valence electrons instead of an octet. That's a lot of electrons. Sulfur can do that because it's a little bigger. These ones in the second period of the periodic table never form expanded octets. It's only when you get down here that they can do that. And so phosphorus is also in period 3, and we see phosphorus can form phosphorus pentachloride, where it has 10 electrons instead of 8. So in Chem 20, we tell you, yeah, these exceptions exist. And then we just go on and look at the ones that follow the rules. So in spite of those exceptions, it's still a very useful model.